physical science time, we're going to talk about periodic table still. I'm going to call this periodic table, oops, let's spell it right at least, table 2. Right, because this is the second time we're talking about it. We ran out of time yesterday. We talked very briefly about valence electrons and how electrons are organized. We talked really effectively, the last thing we talked about was that the periodic table is broken up into vertical, fill in the blank, vertical
columns.
Yes, but those are called groups or families. And then the horizontal rows, which are called periods. Remember that the periods were periodic, that's why they're called that, right? They had repeating patterns of chemical properties of the elements. For instance, and you have your periodic table in front of you, I'm going to be gesturing to this one over here, and then if you're watching online, like hopefully Carter is, you can find a periodic table online or you can use one that's in front of you. Anyhow, the example for periodicity of the periodic table was that, for instance, we had sodium, a light metal, magnesium, a slightly less light metal, and slightly less reactive, aluminum, which is a metal that behaves almost like a metalloid, silicon, a metalloid, phosphorus, a nonmetal, sulfur, a nonmetal, chlorine, a gas, right? And so they all kind of went, and Dmitry Mendeleev, who we talked about, had noticed that if we organize them in order of their atomic mass, which is what he did, they more or less follow a pattern of metal, some number of metals, then some number of metalloids, then some number of nonmetals, and then some number of gases. And then it started over again at metals, right? And so he noticed that pattern, and that drove him, I've heard people describe him as obsessed, where people at the time kind of considered this problem of the periodicity of the elements, they kind of considered that solved, and he continually just kept working on it almost obsessively, and he came up with the periodic table that we know today. And it was so good that his periodic table had what we call predictive power, right? He noticed when he was trying to make it all fit together that it didn't quite work, right? He would notice that there'd be something that the next one really should have been, for instance, a metalloid, and instead it was a non-metal. And so he noticed that pattern, and his periodic table that he devised, he had the bravery, the guts, he had the courage to say, there must be an element missing here. Right? And in fact, later it was found to be true. And in fact, he went further than that, and when gallium was discovered, he predicted the existence of gallium, which is number 31. You see it's below aluminum, right? So in his periodic table, it went right from zinc to germanium. And he realized that there probably should be another metalloid in there. And so he said there will be an element discovered, which he called Eka-aluminum, which was below aluminum. And he predicted it would have similar properties to aluminum, except that he had a certain atomic mass that he thought it would be, and he had other properties, boiling point, density, things like that. And he went as far as to say, when this was discovered, and the man who discovered it named it gallium after his native France, a Frenchman, he published a paper about how he discovered a new element. And Mendeleev said, oh, no, your data is wrong. Even though the guy had discovered the element and had physical experiments to show what his data was, Mendeleev said, no, your data is wrong because it doesn't match my predictions. Which that's pretty gutsy. He published a paper about how this Frenchman was wrong. And then it turned out the Frenchman was wrong. And Mendeleev was right, even though he had never seen the element that this Frenchman had discovered. So the periodic table, the way Mendeleev built it, is a fantastic tool. It's maybe the best triumph of human organizational thinking in all of history, because it flows so perfectly. Like I said before, all of these are physical things that are true in the whole universe, and the way that they're arranged is bordering on artistic, right? It's beautiful that they have this periodicity to them. Because we could just arrange it as a grid, right? And it would be effective, but it wouldn't be as useful as this is. There are so many different ways that this comes together to be useful to us. Do you have a question, Peyton?
So is the periodic table false, or did they fix it?
No, yeah, it was fixed after that. So yeah, the correct properties of gallium were found, and that was true. And this was in the late 1800s, so that was a long, long time ago. And many elements have been discovered since then. And then another thing I want to talk about is that we live, I think, this is to me, kind of a golden age of the periodic table, because you can see it ends very neatly with Oganesson number 118, right? If there were discovered, which there aren't, but if there were discovered 119 elements, which probably will happen someday, we'd have to have a whole other row down here kind of messing everything up, in my opinion, right? It'd make it look less symmetrical and beautiful. Also, you might, if you look in your book,
119 elements.
we just haven't discovered the 119th element. But if you look real quick in your book at the periodic table they give, This was published not very long ago. I think 2010 is when this was published, right after I graduated from high school. But look on page 518 of the periodic table. There's also one in the back. But look at page 518 on your periodic table. You see, especially, I'm talking about the bottom right corner especially. There's a lot of grayed out areas where those elements had not been discovered. You see that? So this is why I say that now, 2021, well really since 2019, it has been a golden age of the periodic table from a visual design standpoint because it's full, right? All 118 elements that we know of now fit very neatly on this periodic table. But not only do we notice that there are some that are missing here, look at 114. What's its name in your book?
Unquadium.
Say it again, Mitchell. Unquadium, right? Which is just Latin for 114, or not really. It's Latin for 114 right? It's basically Latin for element 114. Look now at the modern periodic table. Fluorovium. Right, that's not, I don't know who that's named after, but that's a much better name than unquadium. Right? So not only is the periodic table full, right? There can be more elements, but it's visually full. It ends at the end of the period. Not only that, but also all the elements now, since 2019, have names, which is beautiful. Whereas before, you see unquadium, your book also says unundium. Those are what were at the time placeholder names. So I think this is really fantastic. We have a beautiful periodic table now to look at, and I just love it. This is one of my favorite things in the entire. Like I said, I think it is the biggest triumph of human organizational thinking ever. Now, we had talked about valence electrons, right? So let's talk a little bit more about that. Electrons are organized in what we call energy levels. We did talk about this. We had said that the Bohr model of the atom is that electrons are arranged in energy levels. You might be able to tell just from the diagram, but more electrons can fit in higher energy levels. That's something you probably should write down. More electrons can fit in higher energy levels. There's a mathematical formula to determine how many electrons can fit in each energy level. Excuse me, and it is 2n squared, where n is the energy level, the number of the energy level. So using this little formula, 2n squared, how many electrons, let's just fill in the blanks, how many electrons will fit in energy level 1? Well, what should I substitute in for n?
1.
So 2 times 1 squared. What's 1 squared?
1.
Very good, Wade. What's 1 squared? 1. Times 2, how many will fit in this energy level? 2. Okay, energy level 2, 2 squared times 2, which is going to be?
4 times 2,
8. Energy level 3, 18, etc. Right? It goes right down the list. So each energy level can hold more electrons than the one before. But it's also true, write this down, the highest energy level can only hold 8. Even if this little math tells us that the highest energy level, which here is 4, which would be 32, it can still only hold 8 when it's the highest energy level. Highest energy level is most stable with 8. What did we call this? We had a name for this yesterday. This is kind of review. Octet rule. Octet rule.
How do you spell that?
O-C-T-E-T rule. We talked about this about 10 minutes ago, but what's important about the valence electrons? What's important about the highest energy level electrons? What's important about the valence electrons? No, that's not true. There you go. They determine the chemical properties of the element. Put this down. Valence electrons are the electrons that are transferred when a chemical reaction occurs. I'm going to briefify that so you can write it down more easily. Valence electrons are the electrons. Obviously, their definition is they're the outermost, but this is what's going to be true also. Valence electrons are the electrons that engage in bonding. And we're going to talk about bonding more in the next couple of chapters, but these are the ones that determine when an element will react with another element. Let's do a little science. Let's do a little practice problem here. Look at the element fluorine, number 9. First, let's do like we've been doing in our bell work and what we've been doing in our worksheet. And let's write down this number of protons, neutrons, and electrons, okay? So I'm going to say that we're talking here, let's say, about fluorine 18, just as an example, okay? So write down fluorine 18. Fluorine 18. How many protons, neutrons, and electrons, real quick?
9
Okay,
protons.
9 neutrons.
okay,
9 electrons.
good. In the nucleus here, what should I draw?
9 electrons.
8 electrons. No.
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 9 protons and 9 neutrons. So I'm going to put 9 little plus signs. 4, 5, 6, 7, 8, 9. I'm going to put 9 little zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. The zeros represent neutrons. The pluses represent protons. This is one way we can represent. This is kind of a little concise way. There's no way that someone watching the video is going to be able to see that there are 9 pluses and 9 zeros. There are, so you just have to believe me. How many electrons now? This is where it gets a little bit more complicated. How many electrons? That's not the complicated part. No. 9. There are 9 electrons. But remember what we just said. How many can fit in the first energy level?
2.
Right, because of this. Only 2 can fit in the first energy level. So how many then are in, I'm going to draw these quite a bit smaller actually. How many then are in the second energy level?
8.
No?
4.
No?
2.
How many can the second energy level hold?
8.
8. Remember this, it says they can only hold 8 in the highest, so it's got to have 7, because there's already 2 in the first energy level, so now 7 in the second. 1, 2, 3, 4, 5, 6, 7. How many valence electrons does fluorine have then? Bingo. What group is fluorine in on the periodic table? 1, 2, skip these, 3, 4, 5, 6, 7. 7 valence electrons like we just found, and it's in group, what we call sometimes 7A on the periodic table. Isn't that the coolest thing? No, look. Go on your periodic table right now. That hurt my throat to do that, so I hope you're happy. Look what that group is labeled on your periodic table.
17.
It's labeled 17. How many valence electrons does group 17 have on this periodic table? 7. How many do you reckon the group 15 would have?
5.
That's right. Okay, so some periodic tables are arranged like this, where 1, 2, and then it goes down to transition metals are 3 through 12, then 13 through 18 is up here. But others, you'll see other periodic tables that are arranged, I'm going to draw this pretty small up here, where it's 1A, 2A, 3A, 4A, etc., and then down here are called 3B through 12B. You see what I mean? And they're just different ways to organize the same thing. They're just different ways to organize the same thing, but both of them tell us, just by looking at it, do you think it's just a coincidence that the fluorine had 7 valence electrons and it's also in group 17?
Yes.
Try again, Wade. No, it's not a coincidence. They're all like that.
Periodic.
All of them, listen to me, Allie, all of them, the group they're in matches the number of valence electrons they have. Because of the periodic table? No, the periodic table was designed to illustrate that property of them, okay? Now this has 7 valence electrons. How many does it, I'm going to say 1. How many is it most stable with? You remember from yesterday? 8. It's most stable with 8 because of the octet rule. So it has 7. It's most stable with 8. This is a pretty simple math problem. What does it want? Okay, listen. It doesn't want anything because it's an atom and it can't think. But what would it be more stable? What could happen that would make it more stable? It could gain an electron. Nice. If it gained an electron, how many electrons would it have?
8.
It would have 10 electrons if it gained an electron. And what would its charge be? -1. Why would it do this? To become more stable. Write that down. Electrons can be transferred or shared. Electrons, this is getting into the next chapter, but electrons can transfer or be shared to make, write it down please, Ellie, atoms
Am.
more stable. So that answers the why. Why does it want another electron? To become more stable. Now how does it get another electron? It just walks down to the DG and goes and gets a 12 pack of electrons and only drinks one? No. How does it get another electron? Another atom. What boy up here do you think wants to get rid of one atom, or sorry, one electron?
Hydrogen.
Sure, maybe hydrogen. Definitely hydrogen does in fact. What else?
Any other one?
No, not any other one. What other ones might want to get rid of one electron? One valence electron.
Gas.
Sodium? Yeah. Why sodium? You just guess, or is it you know?
Because it only has one.
Because it only has one. If sodium gets rid of one electron, how many will it have in its outermost energy level? Well, it has one right now. How many will it have in its outermost then? It'll have 8 in its next, right? You see, that'll make sodium more stable, and it would make fluorine more stable. So let's draw sodium up here real quick. We're going to say that this is going to be sodium 22. So right now we're just going to draw sodium 22. Tell me protons, neutrons, and electrons. Can you see that on the screen?
Electrons, 11.
Oh, I think actually that for the first time ever, my picture-in-picture is in front of that. So I'm just going to turn it off for a second. Protons, neutrons, electrons. Tell me.
Electrons, 11.
Okay, electrons 11. That's a weird one to start with, but you're right. What else?
Protons, 6.
No, sodium is Na. You see that
Oh.
there?
11.
11. Neutrons then? You guys remember how to do this? We just did this. 11.
11.
Let's draw it. How many protons and neutrons should go in the nucleus?
11.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then 11 neutrons. 4, 5, 6, 7, 8, 9, 10, 11. You're going to have to trust me again, but that's 11 protons and 11 neutrons in the nucleus. How many should the first energy level have for electrons?
2.
It should have 2. How many should the second energy level have? It can only hold 8, so it should have 8. 2, 3, 4, 5, 6, 7, 8. How many should the third energy level have?
1.
1. Now this bad boy, he's only got one valence electron, right? How many does he want to be happy?
8.
8.
8.
So
Is it gonna be easier for this bad boy to gain 7 electrons or to lose this one and go down to this energy level? To lose 1. So if now listen, just in the same way that fluorine can't go to the DG and pick up a 12 pack of electrons and drink just one, the sodium can't just boot this one electron to the curb. It has to have somewhere to go. Write that down. The electrons can't just come from nowhere, and they can't just go nowhere. They must be transferred or shared. Electrons must be transferred or shared. They can't just come out of nowhere, and they can't just vanish into nowhere. What I mean by that is the sodium can't just think, right, it doesn't think at all, but it can't just get rid of this one electron into the nothingness, right? The analogy I always use is that your parents don't want you to live at their house. That's just the truth. They don't want you there at all. But they feel bad if they just said, all right, Haley, leave. Get out of here. I never want to see you again. So they have to make sure that you're married or have a job or go to college, right? They have to have somewhere for you to go in order for them to feel happy with themselves, right? Think about it the same way as sodium. You can't just say, see an electron and boot you to the curb, right? He has to have somewhere for it to go. It's kind of like when you see in the paper, dogs or puppies free to a loving home, right? They don't want to just take the puppies to the river and throw them in. They have to make sure they're going to a loving home, right? The electron needs to go to a loving home. And where is the loving home? Well, the fluorine wants another electron, so it's going to go here. Check it out. Check it out. So how many electrons now does the sodium have?
10.
10 electrons, giving it what kind of charge?
-1.
No,
No, 1.
plus 1. Now here's the final bit, and we're going to finish. Check this out. We have a positive sodium and a negative fluorine. What do we know about positive and negative charges?
They attract.
Opposites attract. So there's going to be this electromagnetic force, what we call a bond. They are bonded together, giving us the substance sodium fluoride.
Sounds familiar.
Sounds familiar. So this is how some atoms can bond together to form another substance, right? Last thing before we go, I said this was the last thing, but I was wrong. Last thing before we go, we can also illustrate how many valence electrons something has with an electron dot diagram, what we call an electron dot diagram. Well, all we do is we write the symbol, and then we put a dot for each electron it has. How many should I put with the sodium here? Back before it was 9.
11.
No, nope, valence electrons only.
Oh.
And how can I tell?
1.
8.
Just one. Right. I'm sorry, Wyatt. Once again, I'm before it transferred its electron. So when it's normally just an atom, it has one valence electron. What's the easiest way to tell how many valence electrons? You could do this for every one. Put 2 in the first level, 8 in the second, up to 18 in the third, right? You could do that all the time. But what would be an easier way to tell how many valence electrons each atom
To
has?
subtract the electrons by...
No, Mitchell, say what you were going to say.
Just look at the.
Look at the table, because remember the group number matches how many valence electrons. So how many would fluorine have? How would I draw the electron dot diagram for fluorine? F, because that's its symbol, and then how many?
7.
7. Now be careful. What we do is, check this out, Kyler.
Check it out.
We put 1 on each side before we put 2 on it. Okay, we're going to have 7 altogether. We have to have all of them with 1 before any of them can have 2. Does that make sense? So like look at calcium. You see calcium. How many is it going to have?
3.
Calcium is number 20.
Oh. 2.
It's going to have 2. So I would do this, not this. You see what I mean? All of them have to have 1. We put 1 on each side before we put 2 on any of them. This is called what? I just said it.
A dot diagram.
Electron dot diagram. We only put what electrons on the electron dot diagram? Valence. And what's the easiest way to tell what the number of valence electrons is?
That. The number.
Sometimes, yeah, that's, I think that we're going to call it quits there, but sometimes we do, I forget if it's this chapter or the next one. I think it's the next one, or no, it's chapter 19. We're going to, at some point, we're going to go in the lab and we're going to check out all the different elements. You're going to get to hold some of them in your hand. It's so cool.
Gallium.
Gallium, yep. Okay, do you have any other questions?
Wait, 8 gallium.